Welcome to qnawire.
All right, so we have a banked curve, and we want to figure out what angle we need that curve to be set at when we're given the following conditions. We have a mass 1 and mass 2, 11.5 and 2250. We have a radius of 225. Velocity, we want everybody to go the speed limit of 29.06 meters per second, which is the same as saying 65 miles per hour. So I made that conversion so that we can utilize the standard units of measurement. So when we look at a basic model of what's happening as a vehicle goes around this banked curve, what we're seeing is a mass, and I'm looking at it from behind, and it's about to enter the curve here and start going around the circle, is that there is a force that we call centripetal force that's maintaining the circle for this vehicle, and that is always pointed directly towards the center of the radius, parallel to the ground. So here we have our FC has got to equal some other value, because it has to equal a different force, because centripetal force isn't a force of its own. It's like the net force, except it's in the circular world. And so we've got to look at what is the force that's causing this to stay in the circle. Well, it's the push in the X component from the banked surface. So we can say that the centripetal force must equal the normal force in the X component. That is what's causing this vehicle to maintain the circle. So on my force diagram, I would need to figure out the cosine of the angle is equal to the opposite side divided by Fn. Now the net force in the Y component, we don't have this object or this vehicle sliding down the curve or sliding up the curve. So we need that net force to equal 0. So the Y component's net force must be 0. And so that means that the weight of the vehicle must equal the Fny component here. So that's what we're going to do to set this one up. So the first two questions in part A is, does mass matter and what angle are we at? So the first step is recognizing that the centripetal force is equal to the X component of the normal force. That's what's maintaining the vehicle's circular motion. We're ignoring friction, so we're making our angle as if there was no force of friction here at all. So even on the most icy conditions with bald tires, this vehicle, if it's going 65 miles per hour, will make it around the track, around the curve. The other thing that I need to keep note of is that the relationship of the weight and the normal force in this scenario. So if we look at this, the weight versus the normal force is the relationship of this Y component here, right? So the Fg has to equal Fny. So that means that we can figure out what the total normal force vector is by using this trig function. Cosine of the angle is equal to Fg over Fn. We rearrange that to solve for Fn, then we can make this this substitution in our equation over here. So on the left here, I've got the centripetal force equation, mass times the velocity squared divided by r. That's this centripetal force equation. We know that the normal force in the X component is the sine of some angle times the overall normal force, which we've decided, or we have determined was Fg over cosine theta. So I made that substitution over here. So we have sine theta, because we only need the X component, of the total normal force, which is found by taking the weight divided by cosine theta. Now here's this is the answer to the does mass matter part. Notice that on each side of our equation, we have mass as a factor, and that cancels out. So as long as the car and the truck are both going 65 miles an hour, the curve will work for both of them. And thankfully, that's the physics involved. Otherwise, we'd have trucks that had to go at a different speed limit than cars, and it would be a mess on the road. So mass actually has no bearing on what angle to set this curve. So now we're down to v squared divided by r. And if we remember our trig identity, sine divided by cosine is tangent. So I made that substitution as well. So it's down to v squared divided by r equals tangent theta times gravity. So we know everything except the angle now. And so we can solve for that. And we get this. So the angle is equal to the inverse tangent of 29 squared divided by 9.8 divided by 225. So I moved the g over to the denominator on the left. We round this to two significant figures, we get 21. I think it comes out to around 20.9 degrees. So that's part A. Mass does not matter, and the angle is 21 degrees. We set it at 21, and they go 65 miles an hour. They're not going to slide down the curve, and they're not going to fly off of the curve. Now, part B. Now we're going back to our original equation for what we determined normal force was, and I did that up here. The cosine of the angle, which we now know, is equal to the proportion of the weight divided by the normal force. And this is different than what we would have done back in inclined plane, where the normal force equaled FG perpendicular. That's not the case here because there's more to the normal force than in that sliding down the ramp. We don't want the vehicle to slide down the ramp or the curved bank. We want it to stay right here. So we have to have it in we have to have a little bit more for that circular motion to occur, maintain that position. So it's going to be FG divided by Fn equals cosine. So that's what we have down here. I rewrote it, solve for Fn. I get two values because there's two different masses. And here mass does matter. Each of them are going to have their own normal force, but it's all dependent on its weight. So weight divided by cosine 21 for the normal force for the car is going to be around 11,800 newtons. For the truck, it's going to be double that, 23,600 newtons. So the suspension on the truck naturally has to be better than the suspension on the car. However, the road is going to be able, as long as it's made out of sturdy material, the angle that it's set out at 21 degrees is going to be able to maintain the circular motion for any vehicle of any mass, as long as they're going 65 miles per hour. I hope that was helpful. Let us know if you have any questions.